Alright, welcome to another Green Ninja Climate Science Series video. In this video we're going to be asking the question, how can we predict the weather 100 years from now? So you hear this question come up when you might hear of some type of a projection of climate change out to the year 2100, that a given location might experience X change in precipitation or X change in temperature. And people hear that and they understandably become skeptical, because people have a intuitive understanding that weather is very hard to predict, and they know this from watching the local news and getting weather predictions on a daily basis, and knowing that beyond a couple of days the weather forecast is very uncertain. And they're right that past 3 or 4 days into the future, the skill in how good the weather forecast is going to be diminishes very rapidly. So we really can't predict the weather out past 5, 6, 7, 8 days. So the short answer to how can we predict the weather 100 years from now is we can't. That is really not what is being done when you hear some type of a climate projection out to the year 2100. So climate is average weather, and averaged over a long time period, like decades at a time. And it turns out that forecasting a change in the average is actually a lot easier than forecasting these kind of day-to-day ups and downs. And so to give you some other examples and other systems that follow this same rule and make this more concrete, let's talk about, let's say, waves in the ocean. So in this analogy, we're saying that the waves are kind of like weather, and we're trying to predict where on the shore the water meets the shore. So the waves make it difficult to predict where the ocean will meet the shore at any given time, because there'll be big waves and small waves, and it's kind of variable. It goes back and forth over the time frame of seconds to minutes. But in the long term, we have tides, and tides are actually pretty predictable. So let's say over a 6-hour period, you're moving from a lower tide to a higher tide, despite the fact that there's these waves that introduce kind of randomness on top of where the ocean meets the shore. In the long run, you will see this shoreline rise up, or the ocean rise up the shoreline. And that's very analogous to the situation that's going on with weather and climate, that weather makes the temperature of the next day or week or year very difficult to predict. But in the long run, we know that the average weather will increase as we're increasing greenhouse gases in the atmosphere. Another example is just dice. So if you pick up a pair of dice and you want to throw them, and you want to predict what numbers are going to come up, that's going to be extremely difficult. So you would have to come up with some type of really advanced, precise physical equations that relate exactly how these two dice are, or these two dies are going to hit each other and bounce off the table and land, and which numbers are going to come up. And that's a really difficult problem to solve. However, if you roll two dice, say 100 times or 1,000 times, it's actually really easy to predict that the average of those dice will be around 7 when you add them up and average them over all of your trials. You will eventually converge on the number 7. So this is another example where it's much easier to predict the average than it is any given outcome of the trial. To take an example that's more close to the actual physical system that we're talking about, let's talk about weather and yearly temperature. So here's a graph of San Jose temperature. In 2013 is what we're showing. The high and low of every single day is in this dark blue here. And we show the average high of every single day of the year, and the average low of every single day of the year, and the record high of every single day of the year, and the record low of every single day of the year. So you can see that for 2013, we have kind of ups and downs in the weather. It gets hot for a little bit, then it gets cold, then it gets hot again, then it gets cold here, then it's getting hot again. But in the long run, from January through March, the long-term trend is up, because the sun is getting higher in the sky and the days are getting longer, and you're moving from winter to summer. And so I have no idea what the high temperature will be, say, January 13th or January 14th or January 15th. But I know it's very easy to predict, actually, what the average temperature for July will be relative to what the temperature will be in any given day. And so this is the same thing when we're talking about decade to decade climate change, where so again, this is a graph for San Jose, and we're looking at climate or temperature from 1850 to the year 2011, and there's a long-term increase in temperature. Now it's very difficult to predict the actual wiggles. So when people project climate change out to the year 2100, they're not saying that 2100 will be warmer than 2099. They don't know that, but they're saying that the long-term trend, this red line, so the red line's averaged over 10 years, but you might even take a longer average, like 30 years, that is going to continue to go up as greenhouse gases continue to rise. And so we're really talking about, when we're talking about climate projections, we're talking about changes in average weather, which turn out to be a lot more predictable than changes in the weather itself. So how can we predict the weather 100 years from now? We're not actually predicting the weather, we're predicting something that's a lot easier to predict, which is climate or average weather.